reservations in two-way slabs by means of yield lines. We will tackle the problem of the case of 11 to 15, which is a slab on two sides fixed and on two adjacent sides simply supported. This is case 13. Case 13 deals with an edge square hole and not cutting the yield lines. Unless this line on top is an exception to that. Now let's look at the different geometric parameters. It's a two-way slab, so the distance B must be between A and 2A. Square hole D1 equals D2. At the edge D3 is 0. And between the yield lines means that D2 plus D1 or D4, let's put it, sorry, D4 must be between, of course, this portion here, which is S1 over S4 times D1, and at the other side, which is B minus D1 and minus this part here. So now we know that this edge square hole travels between the yield lines, not cutting them inwards. So we have now put some numbers to it, and this is the visualization of the different situations from left, middle to right. We will calculate the work done by the external forces. We look at the green portion, which are the summation of the triangles, which is A times S1 plus A times S3, and the mean deflection is delta over 3. So that's this part. Now we come to the orange part, the rectangular part. The width is B minus S1 minus S3 times A, but we have to subtract the reservation. And this is D1 times D1. And the deflection, the maximum deflection there is D1 over S4. And the mean deflection is half of it. So you can write this as follows. Next, we calculate the work done by the internal forces. And we know that this is B minus where the hole is minus D1 divided by the angle of rotation delta over S4, this one. Then we have this line projected on this axis of rotation, so it is B divided by S4. The other side, it's A divided by S1, A divided by S3, and also here A divided by S3, and last is B divided by B. We fill in the different parameters, and we know that E must be equal to B. We obtain M from that, and this is the formula for M. Notice that this formula is only dependent on alpha and on V1, alpha or alpha 1, only dependent on the size of the flap and the size of the reservation. It is independent of D4. So now there's a danger in it because you can use this formula not knowing that it's not valid. You have always to check D4. The different elements that you got, you must always check that it fulfills D4. You will see to it just right now. First example, you got a rectangular slab with a reservation in it of 1.7 by 1.7. The load is 20 kilonewton per square meter, and floor fin is 2 kilonewton per square meter, and we want to calculate the needed reinforcement. The load in ULS is 1.35 times permanent load plus 1.5 times mobile load. It gives you 39.45 kilonewton per square meter in ultimate limit. We now use the values of the parameters, and use the formula of the previous slides to calculate the maximum bending moment occurring in the slab, which is 26.5 kilonewton meter per meter. We will convert this in reinforcement. We calculate the lever arm in X direction, in Y direction, and the mean lever arm is 150 millimeters. The needed reinforcement is 1.1 times the bending moment divided by the lever arm and the yield strength of the reinforcement. It gives you 500 square millimeter per meter. Using a diameter 10, so diameter 10 every 150 millimeters, X and Y direction, top and bottom will be okay. Of course, you can also choose another diameter instead of 10. So if we use diameter 12, then we need 504 square millimeters, and diameter 12, 5 per meter will then be enough. The second example, you have an existing slab and where the top and bottom reinforcement are the same. You do not know the reinforcement, you do not know the load. And they want to make a reservation, the slab, by top by 1.6 times 1.6 meter. And it's situated on 1.7 meter from the left-hand side. Question now is this allowed? Or what is the effect of the reservation on the bearing capacity of the slab? We calculate first the bearing capacity of the slab without the reservation, but we don't know what the load is, so we divide M0 by the load, and we obtain with the formula 1.112. After that, we calculate the bending moment with the hole or the reservation in the slab, and it gives you 1.107. So this means that the bearing capacity is 100.5, so it's more or less the same. So the reservation can be made without losing bearing capacity. Bearing capacity is defined as 100 times the maximum bending moment without the hole divided by the maximum bending moment with the hole. In formula, it looks like that. We take unitless variables, and we see that the A13 type of hole has this limitation. Now in the formula alpha 4 does not occur. So how do we deal with this? The bearing capacity is then given by this formula. On a graph, x-axis is alpha 1, the y-axis is the bearing capacity, and we do it for alpha between 1 and 2. And these are the different colors. What we notice here is that first we have a limit here, which is alpha 1.634, but this limit is in fact depending on alpha. We will just see how this works. This point, for instance, 1.5, that's the blue curve there. You get here at 0.3 alpha 1, you will have 100%, which is this point. This is that one. But we see that to be valid, this point must be within these limits. Alpha 4 must be between those limits. But alpha 1 in our case is 0.3, so we fill in 0.3, and we see alpha 4 must be between those two values, which is possible, so this result is okay. And it corresponds with those two situations. That is the lower limit, and this is the higher limit. So you have the two limits where alpha 4 is moving between. Now let's look into that now. Suppose we have the blue curve, alpha is 1.5, the blue curve. Alpha 2 or 1 must always be smaller than this one, but because of this reason, we fill in alpha is 1.5, and you see that alpha 1 is 0.582. It means that from this point onwards, here, 0.58, the formula is not valid anymore. So from this value, this is not valid. So it's only the blue curve that is valid because of the limit of alpha 4, nothing else. Then we can go to the square slab at alpha is 1. Then we see that alpha 1 0.388, which is this point, and that means that all this portion is not valid. So only the left portion is valid. Then something that we notice is that from a certain value of alpha 1, between 0 and 0.3 or something like that, the bearing capacity is not changed or barely changed. So that's nice to know. In all other cases, the bearing capacity increases instead of decreasing. So square hole of type H13 has no loss in bearing capacity as long as you stay within the yield lines.